This video is brought to you by mywayteaching.com.
In this part, let us study about Ohm's law. It's one of the important law, a basic law regarding flow of currents. It was discovered by G.S. Ohm in 1828, long before the physical mechanism responsible for flow of currents was discovered. In order to get this Ohm's law, let us consider a simple, you can say, experiment. Okay, you just imagine a conductor through which a current I is flowing. Okay, and let V be the potential difference between the ends of the conductor. Then you know what this Ohm's law states? Then Ohm's law states that potential difference V is directly proportional to the current flowing through the conductor. That is, V is directly proportional to I. V is equal to R into I. So where this constant of proportionality R, we call it as S. We all know this, that is resistance of the conductor. Okay. This constant is called as resistance. And in SI units, the unit of resistance R is given by Ohm. Okay. The symbol is like this. And the resistance R, it not only depends on the material of the conductor but also on the dimensions of the conductor. The dependence of R on the dimensions of the conductor is very much important, or we can say this resistance is depending on the dimensions of the conductor. So, how this resistance is depending on the conductor? Let us see. You just consider a conductor to be in the form of a slab of length L and cross-sectional area A, as you can see in this particular figure A. And imagine placing two such identical slabs side by side, as you can see in this figure, so that the length of the combination becomes L plus L 2L. And the current flowing through the combination is the same as that flowing through either of the slabs. If V is the potential difference across the ends of first slab, then V is also the potential difference across the ends of the second slab, because that second slab is identical to the first and the same current I flows through both the slabs, isn't it? Yes. And now the potential difference across the ends of the combination is clearly the sum of the potential difference across two individual slabs, that is V across one slab and V across another slab. So the total potential difference across two slabs which are placed side by side will be equal to 2V. And the current through the combination is I, isn't it? And the resistance of the combination will, we can write it as RC. Okay, the resistance will write it as RC. Okay. And that is given by potential by current I is RC, which is equal to 2R. R is resistance across single slab, we can say. We know that, right? R is equal to V by I. the resistance of either of these slabs. Okay. So when we double the length of a conductor, doubles the resistance. So here what is noticeable is that the resistance is depending on the dimension length. So we can say R is directly related to L, the length of the conductor. This is the first one. Okay. Now let us consider one more situation. Okay. Imagine dividing the slab into two by cutting it lengthwise. As you can see in this figure C, dividing the slab lengthwise by cutting it into two. So the combination of two identical slabs of length L but each having a cross-sectional area of A by 2. So for a given voltage V across the slab, if current I is flowing through the entire slab, then clearly the current flowing through each one of two half slabs is I by 2. Isn't it? Since the potential difference across the ends of the slabs is V, same potential difference. So the resistance of this half slab, we'll call the slab 1, the resistance of that half slab R1 is given by V, the current flowing through is I by 2, that is given by 2V by R, that is 2R. Okay. So having the area of the cross section of a conductor doubles the resistance. Halving the area doubles the resistance, which means we can definitely say the resistance R is inversely proportional to the cross-sectional area, isn't it? So combining the first observation and the second, we can write R is directly proportional to L by A. So then for a given conductor, R is equal to rho L by A. So where this constant of proportionality, this one is, it depends on the material of the conductor but not on its dimension. So this constant we call it as resistivity. So now we can write Ohm's law. V is equal to I into R, that is R is given by rho L by A. Okay. Current per unit area, we know I by A. This is current per unit area. And we call it as current density. Okay, we will denote it with J. This is called as current density. Okay. The SI units of the current density, I is ampere, area is meter square, that is ampere per meter square. Okay. See, if E is the magnitude of uniform electric field in the conductor whose length is L, E is uniform electric field Okay. In a conductor whose length is L, then the potential difference V across its end, it is given by E into L. So we can write E into L is equal to J rho L, or in other words, E is equal to J rho. So this relation for magnitudes E and J indeed be cast in a vector form. The current density is directed along E and is also a vector J. Thus, we can write this equation as J is equal to sigma into E, where this sigma is 1 by rho. We call this as conductivity, opposite of resistivity. Okay. See, Ohm's law is often stated in an equivalent form of equation. What we have written here, J is equal to sigma E, in addition to the previous equation, that is V is equal to Rn. Okay. Now let us study about drift of electrons and the origin of resistivity. See, an electron will suffer collisions with the heavy fixed ions, but after the collision it will emerge with the same speed but in random directions. We already know this fact, isn't it? If we consider all the electrons, then their average velocity will be 0 since their directions are random. Thus, if there are n electrons and the velocity of the ith electron at a given time is given by Vi. If you consider there are n electrons and the velocity of the ith electron is given by Vi, isn't it? Then we can write 1 by n sigma I is equal to 1 to n Vi is equal to 0. Now consider the situation where an electric field is present. In that case, electrons will be accelerated due to that field. So that acceleration is given by A is equal to minus E by m, where this minus E is the charge, m is the mass of an electron. Now again, consider ith electron at a given time t. So this electron would have had its last collision sometime before t, isn't it? So let Ti be the time elapsed after its last collision and Vi be its velocity immediately after the last collision. Then its velocity Vi, we can write it as Vi minus E by m Ti. Since starting with its last collision, it was accelerated with an acceleration which is given by the equation A is equal to minus E by m for a time interval Ti. See, the average velocity of the electrons at a time t is the average velocity of all the Vi's. The average of Vi's is 0 since immediately after any collision, the direction of the velocity of an electron is completely random. So, the collisions of electrons do not occur at regular intervals but at random times. So, now let us denote by tau the average time between successive collisions. Okay, we call it, we'll represent it with this, the average time between successive collisions. Then we can say at a given time, some of the electrons would have spent time more than tau or some less than tau. So in other words, the time Ti will be less than tau for some and more than tau for some others. As we go through the values of I, that is from 1 to n, the average value of Ti, then it's tau, which is also known as relaxation time. So now averaging the equation that we studied here, Vi is equal to over the n electrons at any given time t, it gives us the average velocity, that is Vd. Vd is equal to Vi average minus EE by m Ti average. Okay. So we know that is equal to 0 E T tau by m, that is equal to minus EE tau by m. So this end result, it tells us that the electrons move with an average velocity which is independent of time, although electrons are accelerated. So this is the phenomenon of drift, and the velocity Vd here, we call it as drift velocity. Okay.